So welcome everyone to this semi-plenary session. So today I'm very delighted to introduce our speaker, Professor Barry Lennox, who is a fellow of the Royal Academy of Engineering and also a professor of applied control and nuclear engineering decommissioning at the University of Manchester. Before joining Manchester, Professor Lennox did his bachelor and PhD at the University of Newcastle. He then spent some time as a research associate there before he moved to Monash University as a research fellow, and then he joined Manchester University as lecturer. He holds the Royal Academy Chair in Emerging Technologies, and he's the director of the Robotics and Artificial Intelligence for Nuclear Research Hub, which has received £15 million funding, and it's been the center of many impressive achievements, including Karma, which is the first fully autonomous robot that has been deployed in an active facility at Sellafield. They've done a lot of very impressive robotics work there, but Professor Lennox's activities don't stop there. He's involved in many programs, including a multi-million EPSSC program grant on robotics for nuclear environments. So it goes without saying that Professor Lennox has a very impressive track record in control applications, and in particular related to robotics in hazardous environments. So I'm very much looking forward to this talk, which is on design and deployment of robotic systems in challenging environments. So without further ado, I'll let you take over.
Thank you. Yes, well, it is an honour to do this, and I think I went to my first ECC in 2002, and I'm afraid to say I still don't understand H-infinity control. So if you're expecting lots of equations at the end of the day, you might be a little bit disappointed. So I'm going to talk more about the applied work and applied control systems. And although it's challenging environments, the focus is nuclear because that's the area I work in. There's some idiosyncrasies to nuclear which may make it a little bit unique, but a lot of the things are applicable to any kind of challenging environment. And most of it is work that was done in this RAIN program, and we have a really nice logo, so I like to show the logo. So I'm going to start, it's going to be a little bit different perhaps because we're going to go through some a background to nuclear and why nuclear is a problem, why we've got challenges in nuclear. And then I'll go through some of the robots we've been developing, some of the solutions we've been developing, and I'll try and highlight some of the things where we need control, optimization, system identification as I go through. So you'll all be familiar with this, but to explain why robots are needed in certain situations, you'll remember from school, and you know, maybe some of you were trained physicists, so you'll be able to prove me wrong. But you've got three main types of particles: alpha, beta, gamma. Alpha's stopped by a piece of paper. It's very harmful, but only when you ingest it. Beta are their electrons and positrons, and they'll be stopped by a sheet of aluminium, and they do cause some damage to the skin. And you have gamma, and gamma is probably the heart of the challenge that we have. Gamma will penetrate through large dense materials, so it goes into your body and it causes damage. So a lot of nuclear environments will have alpha, beta, gamma, and depending on which things they have in there, sometimes it means that people can't go in at all. Sometimes it means people can go in, but they have to wear a suit. So if it's alpha, people can go in, but you don't necessarily want them to go in. And this is really why we have issues with nuclear, and it's really down to uranium. So with uranium, it has three isotopes: 234, 235, and 238. And to produce energy from them, you not sure if this works there. So you hit a uranium 235 with a neutron, it splits, and you get energy. And you also get extra neutrons, and they go and hit other uranium atoms, and so you get a cascade and lots of energy coming out of it. And that can be harnessed to create nuclear power. It can also be harnessed to create atomic weapons. And you can see that only a little bit of uranium, natural uranium, is this uranium-235. So in weapons programs, an emphasis is on trying to enhance and enrich the uranium-235. So if you've seen Top Gun Maverick, recently. The bad guys in Top Gun Maverick were enriching uranium so they could make weapons out of it. The alternative one, and this is the approach that we took in the UK after the Second World War, is you get uranium-238, you bombard it with neutrons, and that produces plutonium, and then you can make plutonium weapons. So that's the general theory. This was the pile reactor, and this was the first pile reactor. It's a drawing of it. So this is the reactor. It's made up of graphite blocks, and the graphite blocks are there. They slow down the neutrons. You've got uranium fuel in there, and so it's producing heat. And this was the first controlled release of nuclear energy. You've got control rods which drop in and they absorb all the neutrons if there's a problem. You can see here there's a rope and there's somebody with an axe, and their job was if there was a problem, they would cut the rope and the control rods would drop in and stop any nuclear reaction. And it's said that that's where your SCRAM systems come from, safety control rod axe man. So the problems that you get, so inside this pile reactor, you get plutonium being produced. And what you would then do is you have lots of laboratories and processing facilities to extract that plutonium so that you can then make it into in weapons or whatever else you wanted to do with it. And this is where we did it in the UK. So this is an image of the Sellafield site. It's about 1 square mile, lots of great big concrete buildings. Concrete's great because it acts as a shield. Lots of buildings, reactors, there's old processing plants there to extract these materials, laboratories where people were looking at these materials for the first time and trying to understand them better. Now there's no working reactors on there. There hasn't been working reactors for a long time. It's just a decommissioning site. So what we need to do now is to demolish this, make it safe, and extract all the radioactive materials which are still on site. And there are still lots of radioactive materials on site, so we have to safely extract them, store them, and reduce the harm. Most of the things on this site were designed to last for 20 years. That was all developed in the 1950s, 1960s. Well, it's now much more than 20 years. So there's been damage to those buildings and structures. And so there's a real emphasis now, a real need to try to speed up the decommissioning of it so that you don't have additional problems. So it's costs a lot of money. And what we want to do is develop robotic systems that can go in there and reduce people's harm so people don't have to go into the site to decommission. And this is how some of the decommissioning is going on at the moment. So on the left, this would be an old alpha contaminated laboratory. People go in, you can see they're in air-fed suits. They've got an angle grinder and they're trying to cut through a piece of metal. So they're trying to chop things up so you can store it into a small volume. You don't want things stored in great big volumes. Problems with that is that if you slice through your suit, you then potentially get potentially get alpha contamination through the suit. You could ingest alpha contamination, and that would cause health problems. The middle shot is old glove boxes, and when you're experimenting with some of these materials, you put your hands in the glove box and you'd play around with the materials. These glove boxes, there's hundreds of them on site. They need to be chopped up and they need to be decommissioned. One approach to doing that is to get somebody to go in. Most of them have glass screens, but the glass has become opaque over 50 or so years. There have been examples where people have put their hands in and they've sliced through gloves and they've got contaminated by radioactive materials. So if we can try to remove people from these facilities, that's a lot safer. On the right is an example of a processing plant, and this would have beta and gamma, so different liquids would have flown through this, and you now have within those pipeworks and within those vessels, some of it will be contaminated, some of it will have radioactive materials, some of it will be quite clean, and it might be that people can't go into that facility because of some of this gamma material. Some of the facilities you might just be able to walk into. So it's trying to develop robots that will support this decommissioning. You've also got submerged areas. So this is an example of an on-site pond, great big pond, few meters deep, and all these skips in here contain radioactive materials. you have to remember that in the 50s, 60s, 70s, there was a big rush really to keep up with the Soviet Union and the US in developing radioactive nuclear materials. And so they know roughly what's in these facilities. They don't have all the details of what's in these facilities. And so what we want to do is develop robotic systems that can go in here and tell the people exactly where the radioactive materials are, what materials there were, and to allow them to better plan their decommissioning. And it's not just the UK. You've got similar sites in America, in other countries. You'll all be familiar with Fukushima Daiichi. This is the 4 reactors here, the main 4 reactors. There's 2 other reactors over here which were unaffected, and this was after the problems caused by the tsunami. 3 of the reactors exploded. One of them didn't, and now these are having to be decommissioned. And what happened at Fukushima? You have a big stainless steel reactor. This contains the uranium fuel. There was no cooling water going to it, so the uranium fuel heated up. It then, the fuel melted through the stainless steel vessel and dropped down into the, what this is called the pedestal, and it dropped down in here. This is submerged in water. Again, the water keeps it cool, it also shields it. And so what they now need to do in Japan is to get robotic means so they can extract this fuel and remove it from the reactor. And you can see that this is progress. This was immediately after the accident. It's now 10 years later, and it is in a much fitter state. It says now, the photo was a few years old, so it's not quite now. So that's where we came in. So we established this RAIN program funded by UK Research and Innovation. It's quite a large program. It's about 30 researchers, 30 postdocs, and about 30 academic staff. And some of the people are here. So these are the people that have done all the work. It's 10 universities and the UK Atomic Energy Authority's RACE Robotics Centre. And we were trying to provide that bridge between what people are doing in academia with the robotics to what industry need. So there's a pull from industry, but there isn't a supply chain that is developing these robotic solutions. So I said we were looking at mainly Sellafield. This is Dounreay. You'll notice they're all in very remote parts of the country. Dounreay was where we were developing fast breeder reactors many years ago. That needs to be decommissioned. Sellafield has a decommissioning lifespan of over 100 years, so it gets me through my career, and everyone here will still have a career if you want to work in the nuclear industry. It's not just these, so these are just old sites. We're also interested in fusion. Fusion is potentially fantastic, but these things are really radioactive. You can't just walk inside them. You do need robotic systems to go inside them. And new build reactors. We still need monitoring and surveillance of reactors and new reactors, and better to use robots to do that. So I'll go through remote inspection. This is where we go in and we survey or we inspect a facility, and we look at it in 3 different parts: developing the platform, the sensing and perception. So what the robots are is just platforms. The platforms to put sensors on. We take the sensors in, and then we do things with the sensors. And what we want to do is a high-level system which does the mission planning, and it tells the robot where the robot needs to go. So these are some of the platforms we've been developing. I'll go through these a few examples with each of them, but it's a mixture of some of the robots. This one up here, it's a commercial robot, and we put the sensors on, and we get support from different universities who have expertise in different sensing. And some of them are bespoke. So this is a design that we've developed ourselves, a floating platform. This is a Stewart mechanical platform developed by Nottingham. So I'll go through with some examples of each of these. So this first one, this is from Oxford Robotics Institute and a small company called Createch. You've all seen a Spot robot. It is a brilliant robot. One of the problems with Spot is that people look at it and then just make the assumption that robotics is solved, because it is really, really good. It doesn't do everything, but it is a brilliant platform. So what's happening here is Spot is being manually driven around this this processing facility. So somebody's got a joystick and are just moving it around. It can go up and down the steps, and as it's going around, it's building this map. So it generates a map, a multi-floor map of the facility. One of the issues that you get with a nuclear environment, this is a nice clean environment. There's no active materials. The problem with a radioactive environment is that the robot itself can become contaminated. It doesn't become radioactive itself. It becomes contaminated. It might pick up plutonium powders or other materials. That means we can't take them back to the lab. So once you've deployed a robot onto a site, often we can't get it back, so you lose it. So in this case, you might be losing £100,000 piece of equipment. So we want the robots to be low cost because they can then be disposable. So here it's got the full map of the facility, and what we then might want the robot to do is to go back in the future. So you might want it to weekly, daily go back and survey around. So here it's set up so it's got a route that it wants to go around, and then you've got waypoints, and you can program the robot to do particular things at those waypoints. You can ask it to take a measurement, and then you can do data analysis where you're comparing that measurement with measurements you might have taken in the past. So these are the kind of sensors. This is the LiDAR, which most of you probably be familiar with, where this is where you get the 3D images from. It sends laser pulses out. This is an example of a radiation detector, and we also put photonics equipment, and it's any equipment that can give you a better idea of what materials you're looking at. This is one of the few robots that's actually been on a nuclear site and done something that is well, quite useful. So robots aren't used that frequently in the nuclear industry. This is one robot that we developed at Manchester. It was used up at Dounreay, and the purpose of it was that at Dounreay they had an underground duct. It's 150 meters long. It sits underneath this corridor. It's got about a meter of concrete separating the duct, the tunnel, from the corridor. Nobody had looked through this duct for about 20 or 30 years. There are occasional access points every 20 meters or so. There's an access point, so you can lift it up. If you put the containment around it, because you've got materials in here that could cause problems, so you'd have to put containment around it, lift it up, and then you could have a look in. So we developed this robot here to explore along this corridor. So it's got a tracked base. We developed this. It's got a manipulator arm which it lifts this puck up to take swabs. It's got 4 or 5 detectors on the back of it, and it's driven. It's wireless. You weren't allowed a tether because the tether would be quite thick and it would pick up contamination, and so it couldn't be cleaned. So you will see. I'll show you a little video in a minute. But this has got a fishing line. That was considered thin enough that you could then, if there was a problem with it, you could pull the robot back. So the problems come down to, can you get this robot back? So if it breaks down, then you've got real problems, because you can't just go in and pick it up. If it breaks, it's a very expensive problem. So this now shows the robot going in through this duct. So it's lowered down. We're not allowed to do the lowering down of the robot. It goes in behind containment, and it's operations staff that do all that. So we have to shout to them through a plastic cover. So here it is going down. You can see the hook on it, and that's for dragging it back if we get into problems. And it's really a method of last resort. You can see there's a bit of rubble. There's gloves, so discarded gloves over here. And so what they wanted was to get an understanding of how much radioactive material was along this corridor. It's terrifying when you're driving this thing. So it stopped here because there's a load of rubble, and we have to make a judgment. Can we drive it over that rubble, or will it get stuck? If it gets beached, we then have the potential problem that it's stuck. And if it gets stuck, then we're in a lot of trouble. So my approach to it was I drove at full speed over the rubble, and thankful, but it's quite scary. And here we're taking a swab sample. So, and what I'd like is, this is quite a difficult maneuver. It's all done remotely, teleoperation. What we want to do is make these systems more autonomous. We'd like this to be done with an automated system. So you press a button, so it picks up the swab and it automatically rubs it on a surface. And then it puts it back, it brings it back, and then an operator can take that swab out and take it to a lab. I'd also like to know, when we encounter some rubble, I'd like to know which route we should take over the rubble. We'll probably be doing the driving, but it would be nice to be able to say, well, this is the route you should take, and you will get over it without any problems. This is a similar robot, but this time it's an off-the-shelf robot, and it's gone now. But what you can see is all this plastic covering. This is going around a fusion reactor, jet fusion reactor at just outside Oxford, and it's covered in plastic. And the reason for that is that around a fusion reactor, you'll get gamma, you'll also get neutrons, and you also get beryllium dust, and beryllium dust is really toxic. And so you put the plastic coating around it with the expectation that if it picks up any dust, you can remove the plastic coating and you should still be able to take the robot home with you. The one that we deployed at Dounreay, that is now still at Dounreay. It will always be at Dounreay. We'll never get it back again. So we lose however many thousands of pounds that robot is. This one, they needed it back, and it's a cleaner environment. And so it gets a scan of the environment, and it also measures the radiation at various points, and that's to confirm physicists' models. So the physicists have an idea of what happens in a reactor, and this is trying to confirm what they think happens. But the radiation that you have, it affects people. So gamma radiation in particular, you can't go into a gamma environment for any sustained period of time because it will cause health problems. It will kill. It also damages the electronics within robots. So in many environments, what we have to do is, if you've got radiation in the corner, those of you at the back might be fine because it attenuates. It doesn't travel all the way to the far ends. Those of you a little bit closer, you'd probably get you'd have health problems. And so what we try to do is we try to map the radiation without going into those radiation areas. So if we're autonomously scanning an area, so this is some work we did in Australia with CSIRO. What we want to do is, this is an indoor area, and this is a photo of the indoor area, and an outdoor space, and we have a few simulated radiation sources. And what we want to do is to get the robot to navigate around, explore the area, work out where the radiation is, but we don't want it to travel through the radiation, because if it travels too close to the radiation and stays in high dose rates, the electronics get damaged. So we need autonomous systems and control systems so that it knows where this radiation is and it can avoid them. And this is the map we get. So the red blocks represent radiation, and you can see that the blue is the route that it took. So it's an odd route that it sometimes takes. But here it went through here. It measured there was radiation. Next time it needed to pass near this spot because it wanted to go up here, it avoided that radiation area. So we just set up these. We set up cost maps, so we avoid obstructions. We work out where the obstructions are, and we try to avoid the obstructions, and we also try to avoid the radiation areas. It's a soft constraint because we can go into those areas. We just don't really want to. And this is I suppose this is taking it to the other extreme. This is a robot. Here it's got radiation detectors in. It's fully autonomous, and here it's detecting alpha radiation, so it's got to be very close to the ground. It's got to move very, very slowly to detect alpha contamination. It builds up a map. It autonomously knows where the walls are. It autonomously works out which route it should take to cover all the floor space, and then it navigates itself around. And on that map, you could see there were some red patches, and that's where it's identified that there's some alpha contamination. So this is an area where people can go into. But you wouldn't necessarily want people to go into because it's potentially alpha contamination. So again, with this, it's the control systems. We need to develop the control systems, which it's not too complicated in this case. We're just following a path. We've got optimization systems which need to be able to detect that there is radiation ahead, and so what path do we take to get around those radiation patches? And then another thing which we want to do is we want to try to map some of this radiation. So we use Gaussian process regression to be able to do this because we get sparse measurements of radiation. So these might be the measurements of radiation that we get. It takes time to take radiation measurements. So you sit in one location, wait for a little bit and go elsewhere. And if we do linear interpolation, this is the kind of map that you'd get. And what we want, we know that radiation looks something like that. If you've got a source over here, it attenuates quite nicely with an inverse square law. So we use Gaussian process regression to generate these radiation maps. And this is, as far as we know, this is the first time a robot has gone around an operating nuclear reactor. This is a nuclear reactor that's in Slovenia. It's very low powered, but this is the wall of the reactor. This is the robot that we sent in there. So when the reactor is switched on, you're not allowed to walk around this area because you have radiation risk. So we got this robot. This is a detector here. It's got various other detectors on it. And you can see we drove it around the reactor and it took measurements, and you can see that it's taken some dark blue means there's very little radiation, no radiation. And you can see some red spots, which is where there's a higher radiation level. Then using Gaussian process regression, we can get an accurate map of where the radiation is in this facility. So this is the reactor here. This is a plug that's been taken out of the reactor. So the reactor has a thick wall, and they've taken the plug out. And this is the location of the plug. This is a shine path. So you take that plug out, and then there's a shine path. So you can get gamma going straight across to the wall over here. And there's a couple of bottles here of contaminated water. So it accurately detects where the radiation is, gets a nice map. And with Gaussian process regression, what's nice about it is you get a map which gives you confidence. So here we've got lots of confidence in where it's dark blue. We've got lots of confidence in the measurements. Here you can see that we have little confidence, and that's because we didn't take many measurements over this area. So it looks like there's no contamination here, but you probably want to go into those areas and just to check, because you haven't got as much confidence. And so we developed the algorithms which automatically go around these facilities. We also look, I showed you earlier that you had ponds. So we're also looking at developing robots to go into those ponds. This is one that that we've developed. Rather than wheels, it's just got thrusters on the bottom. So it's the same control systems go on it as with the wheeled vehicles. What you do need for this is a big pond. We don't always have ponds available. So this is a land-based simulation of it. So it's got these omnidirectional wheels, and now you can see as this person is moving it around, it behaves like a boat. So it has momentum and it moves around like a boat. That means that we can develop all the control systems on here, and then every now and again we can go to the facility where we have a great big pond of water, and we can put the control systems and test out the control systems on the real environment. So it just allows us to work in a lab in a much easier way. And this is that platform as it moves around the pond that we've got. So this is the platform. It scans the wall, so it works out where the wall is. It works out a route for it to follow, and then the robot would just go up and down and follow that path. What this was designed for, it was the IAEA, the International Atomic Energy Agency. They go out and they have to check storage facilities where you've got nuclear material, and they need to check that in ponds you would put the fuel assemblies, so the uranium fuel would be in a pond, and they need to go in and check that that nuclear fuel is still in there. And so this would just goes up and down and checks that the fuel is there. And this is the control systems that we get for us. So one of the problems is that we want it to be autonomous. So we just want to chuck this platform in, and we want it to go up and down. Its dynamics will change as the payload change. So you put a new weight on it, and it might behave differently. So what we do is we drop it in a pond, put some excitation in it. We've got a mathematical model of the robot, and we can then we either fit a classical parametric model using least squares, or we can do something a bit more complicated and use neural network models. This is the training data, and this is the testing data. So the neural network, you'd expect, it works a bit better than just using least squares. So we can then auto-tune the system. And this demonstrates, so this is the path that the robot followed. We wanted it to follow this square lawnmower pattern. and you can see it deviates. It's a PD controller that's on it. And what I would ask is, a constant source of frustration is, firstly, PID control works really well most of the time, and there's all these brilliant controllers that are developed. PID normally is good enough. In here, you can see all it needs really is a predictive control, and you'd get a really nice tight fit to your set point. What I found with the more applied robotics engineers, the maths is my level of maths, it's not your level of maths. And so if you make things simple, they'll apply these fancy control algorithms. If it's complicated and lots of maths, they're not patient enough to go through all the maths and implement it. And so if you've got fancy control systems that you want to see applied, make the software available, and then you'll get more uptake from certainly from robotics people. This is a robot that we've deployed at the Sellafield site, another submersible robot. Had to go through a 6-inch hole, so it goes in through the 6-inch hole. This was its first prototype on the right here, and the prototype had little thrusters at the side, little water pumps, so it could finely tune and move around inside the facility. What was a bit frustrating, so this went into one of the facilities on the Sellafield site, and they use it as a battering ram. So they just used it to bash material around inside this silo, which was a bit frustrating. Lots of work, and they're just using it as a battering ram. And this is the test in Japan to support some of the Fukushima work. And this is a sonar on the bottom. And what they wanted was the sonar to get a measure of where the metallic, the molten materials were at the base of the reactor. And this is probably my favorite robot. So this is, again, what you have in the nuclear industry is they will drill small holes. You don't have lots of doors to open and go in because these are hazardous areas. So lots of concrete, lots of thick concrete walls, but they will drill a hole through a wall for you. So this robot is designed to go through, it's about 120, 130 millimeter ports. Initially, they said, can you develop something that will go through a 6-inch hole? And we did it, and then he said, oh, sorry, our 6-inch hole is actually about 140 millimeters. So we have to redesign it. So this is the robot. It's got joints here and here, so it can go in a long straight line, and then it can curl up. It's got some really complicated control problems on it. As you move these legs around, it has different levels of controllability, and the problem that we have is that a lot of the weight is in the back here. So when it's in this U shape, these two omnidirectional wheels are off the ground, so you don't get much traction there. So you have areas where it doesn't control particularly well. So we've got lead weight here. So we either use lead weight or we leave it as it is and constrain the controller so that it doesn't go into those particular regions. And this is the robot doing. This is it entering a facility, so it goes through a 6-inch, 140 millimeter hole, I think in this case. So it goes in, and these are the clever little omnidirectional wheels. Once it's in, it's much more stable in its U-shaped configuration. It's got an arm here that will lift up, and that's got a LiDAR on it, and it's got other radiation measurements. You want the radiation measurements to be off the ground. And then we've got control systems, or it can be manually operated. But the other benefit of it is in really highly congested environments, it can snake around and it can move around, and it can go through these areas. And this is what you get out of it. And so this is a scan of a facility. It was the first robot to go into this facility. The door hadn't been opened in this facility, or nothing had been in for 30 years. So they didn't know what to expect. These facilities often are sealed up, and they don't know what's inside. And you can see, well, there's a ladder been left here. There's lots of rubbish on the ground. They're almost always dark. So it might work if yeah, so it is a video. If you want to see it, it is on YouTube. And so you can look around, and it's got a full 3D image of the facility. And again, that helps them with future decommissioning of the environment. And then what we're also able to do with this robot is we've then got complex control and optimization routines to work out, well, here's a congested environment. We've got these obstructions. We've got a path that we want it to follow, and we might want to do particular activities, particular things at certain points. And so we can work out the pose and the route that it should take through this environment. I showed at the start that you have lots of glove boxes in the nuclear industry, and there's two aspects to glove boxes. We sometimes just want to operate and move things around in glove boxes, and other times we want to decommission and we want to get inside the glove boxes, empty them. So if you imagine you left work one day, came in the next day and they said, no, that facility is no longer in use, it's sealed off, and you might have left things in there. You'll have probably left your experimental equipment in there. So that all needs to be emptied out. But that happened 30, 40 years ago. And so there's lots of things in those glove boxes. So rather than putting hands in the glove boxes, we've got manipulators that are going into this glove box. It's all, in this case, it's all teleoperated. So it's controlled by these two big joysticks, and they have feedback on them, so you can sense what you're doing. It's actually, we found it a little bit easier if you have a second manipulator that is the same as this. You move the manipulator itself outside, and this one moves in sympathy with it inside, and that's a little bit easier to use. So this is all teleoperated, but what we want to be able to do is to make it easy for the operators. So the operators, we want it to be as autonomous as we can. It's a highly conservative industry. They don't want things to be autonomous. I think control is brilliant, because I think you have a problem at the moment that people are moving to machine learning and these deep learning things, and you have a black box, and you go along to the nuclear industry and say, my control system uses this brilliant black box, it solves all your problems. And they will say, well, what does the black box do? And how do you know it's always going to give you the correct answer? The nice thing about most of the control work is it's all written down. You've got formulas for it, and it's explainable. And that's a really strong point about control systems in this industry, that things are explainable and therefore they're more attractive to be used. So what we're trying to do here is develop low-level control systems so that the more mundane things, that some of the tricky things can be done automatically for the operator. So here we've got an object that we want to pick up, and we work out different poses of the arm that can then grasp it at the right point. So we can work out where it should be grasping. We would then work out how the arm should be moved and where it should be positioned, and then the operator would click on a button and say, I want to move it there, and then it would automatically do it. So you'll see it's picked it up, and this is a digital twin of the actual system. So it's working here in digital form, but it works on the real system. And so the object is here. It's got two cost functions it's trying to optimize with these two different poses that it does with the arm, and then it picks which the green one in this case. And then lots of other things. This one's straightforward. These things are going to be used. So the presentation earlier about long-term autonomy, these things have to be in place for years and years. You can't go in and fix them because they're contaminated. So it's a health risk to go into fix them in certain situations. So we can have things which sense when things aren't operating correctly, and then hopefully we'll have some fault-tolerant control systems in there. So if we lose degrees of freedom, we can still operate them. This is trying to be able to operate things a little bit better. So here, VR glasses, and this is the well, the view from these eyes would be the view that they get. But this is the virtual world. This is the real world, picking up cans of beer, and they've got a real sense camera on the front here. And so as they move their hand, their bare hand, then this gripper moves in sympathy with it. And so, yeah, so we're developing a control system so that you can cope with the delays, because you don't want to be right next to it. You might want to be some distance away, so there's some communication delays. And this is a snake robot developed by Nottingham University, and this can thread its way into some of these glove boxes. It's a tendon-driven arm, and so again, it's really complex control systems that you need to work out, well, what tendons should you pull? It's got, I think, 27 tendons on it. So what should you pull to get it into a particular shape so it can snake around and go into some of these areas? And we also want to, we're aware that what will be necessary in the future is you've got lots of robots that you're trying to control. So a lot of the robots I've shown you are inspection robots. That's because that's probably the first thing that you'll apply. You'll apply robots to do inspection because they can do less damage inspection. So here's the user. This is the view through the virtual reality goggles. These are supposed to be the robots, they're simulated robots. So they make hand gestures and it tracks their hands, and that's with this this camera on the front. So it tracks their arms. What we'd actually like to do is we've got cyber gloves. So cyber gloves give you a kind of feedback, so you know when you're gripping onto something. Unfortunately, the camera doesn't work, and it can't see your hands and your joints when you're wearing it. So here, what we're doing is just moving around and looking at the robots, and you can pick a robot up and essentially you change the set point of it, so or the position you want it to be at. So here, picking it up and moving it somewhere, and then it will move in sympathy with it moves to that particular position. And I think it should then move on to a zap forward. It might not let me. No, I'll leave it. But you can. So we've got this in a digital world, but it also mimics in the real world as well. So this goes into the real world. So you've got 3 robots here. So you're controlling them in the virtual world. So as you move things around here, you can see the real robots are moving in sympathy. So it's connected to you're in the digital world, and it's connected to the real world. So it's what we're looking at is how to make these things simple so that your operations staff who don't want to spend months and months trying to learn how to use these pieces of equipment, they're not big Xbox users. Some of them might be, but they're not familiar with computer gaming things. And so we're looking at how we can make their jobs a little bit easier. And here we've got, so this is some of the control systems work that we're doing with manipulators. So again, what we're trying to do is to make things easy for the operators. So over here, we've just got a manipulator that's moving backwards and forwards. And what an operator might want to do is to move it around to get it to a particular endpoint, but you always want to avoid colliding with things. These things are really delicate. You think of some of these facilities, they're 40, 50 years old. They're designed for 20 years. You don't want to be bashing them. So here we've got 3D stereoscopic image of the environment. And so when we get our nice mayonnaise bottle, I did suggest them they use maybe sensible things to try and avoid. So we have a mayonnaise bottle, which has appeared in that view. And so the robot needs to automatically detect that. And although you want the robot to move along, it needs to be able to detect and avoid that obstacle. So it's the low-level systems that you're trying to implement so that the user finds it an awful lot easier to operate. And then over here, we've done tests with people. So this is in the digital world, but we translate onto the robots themselves. So you've got an environment where you've got objects and clutter, and we want to go in and grab this object here. If you do this manually and you're trying to look through on multiple screens, so the way that is typically done, multiple screens with different viewing angles, and you work out how you should move the arm. It's an awful lot easier if you have a low-level system where all you're doing is saying, well, I want the arm to go there, and it's then sorting out how it should move the joints so that you don't bash into it. So here, as you move the arm up here, it will just collide with something. Here it works out that it's going to collide, and it does some low-level control systems to avoid that collision. The other thing I mentioned earlier was that radiation does cause damage to all these systems. So if you've got anything that is silicon-based, it's not going to last forever in a gamma environment. So you're, as a human, I think, off the top of my head, I think your allowable radiation dose, and it's a total dose for the year, is about 20 millisieverts. So after 20 millisieverts, you can no longer work in a radioactive environment. If you're a robot, you can survive up to, a human can survive up to about maybe 8. After 8 sieverts, humans will die. So your maximum allowable dose is 20 millisieverts. If you're a robot, most electronic systems that we've tested will survive up to about 50 to 100 sieverts equivalent. They call it grays in SI units. And so the robots can last an awful lot longer than humans can, but they will get damaged in very high environments. So this is a cobalt-60 gamma irradiator. It's like a big microwave oven. You put your thing that you're trying to test in here. In this case, this is an upboard. So we want to test how long this processing unit will last. So we put it inside here. We close the door. You can see it's a lot of lead. It's a very heavy piece of lead. Inside here is cobalt-60. Those rods, when you close the door, they shoot up and they fire gamma at this upboard, and we look to see how long it will survive. So when you see the Juno spacecraft, for example, which has gone up to Jupiter, that contains very sensitive components. There's lots of radiation around Jupiter. It's different radiation than you get in the nuclear facilities, but what they have is a tungsten box. They call it the vault. Inside is all the sensitive components. So we've been looking at, well, we want to use cheap components. So can we use this upboard and surround it with tungsten so that it would shield it? Fortunately, what we found is that you'd need about 20 kilograms of tungsten to shield this so that it would last a reasonable length of time in some of the higher dose environments. So yeah, there's still problems, but we know now how long some of these this equipment will last, and we know ways in which we can improve its survivability a little bit. So essentially, that's a kind of summary of some of the things that we've been doing. We need loads of there's loads of work that needs to be done. We need robots that are reliable. We need robots that will operate really simply without people having to understand the complex control systems. Very few people understand all the complexities of the control systems. So if we want them to be used, they have to be made simple. We want more intuitive HRI, human robot interfaces. The low-level systems, we want them to be automated, so you can just click on things that will go and pick it up. And you've got a lot of things which will just go and grasp objects. Decision support. So we're not going to get full autonomy. The nuclear industry isn't going to allow full autonomy anytime soon. So it's decision support, and it would say, well, you should do this first. The robot should go over here first, and you'd say, yes, I agree with that. So I don't know if you've ever seen a Simpsons sketch where it's got a nodding thing. Duck or something that just keeps pressing a button, and that's the idea. The operator would just keep saying yes, 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 that seems sensible. And I think for control systems, it's this reliable and explainable and trustworthy autonomy. So we need to be able to explain what the autonomous systems are doing, and you can do that with the modern control systems. Communication lags are a problem. So when you're operating these things, teleoperation is communication lags, and we want to reduce that. We also know that these robots, they are going to suffer problems. They will break down. Can we have redundant systems on them so that if they break down, we can still extract them? They might be extracted really slowly, but can we get them out of the facilities? And we want electronic systems to be resilient to the effects of radiation, which isn't a control problem, and it's quite difficult. So that's it. And there's some of the sponsors, and there's probably more which I've forgotten to put on, but they're our main sponsors. So thank you. I hope it's no maths, but hopefully it's given you some understanding of what problems we have in nuclear.